Okay guys, today we're going to finish up chapter 5 with this topic. It's called reaction mechanisms. So before we start, I want to make sure that you've got your chapter 5 guided notes out. We're going to be filling out a little bit of notes as we go through these slides. And that should be it. You just need your notes for this. So let's get started. A mechanism is a detailed model that shows how a reaction occurs. Sometimes reactions, when you just look at the equation, it kind of is a little bit misleading. They look very simple, like it happens in one step. But as we're going to see today, sometimes there's many steps involved in a chemical reaction. And so we're going to look at the mechanism or the detailed step-by-step model that shows exactly how a reaction will occur. So knowing the rate law, so we've been studying the rate law for the last few lessons. But knowing the rate law for a reaction helps us understand the sequence of reactions in the mechanism. For example, this reaction here, which it says the reactant is A, and it goes to product D. If you just look at the chemical equation, it looks like it's very simple, just a one-step process. But actually, this can happen in 3 steps. So if you look at the mechanism for this reaction, it might have 3 steps. And so let me put those steps up here. Where A goes to B, and then B goes to C, and C goes to D. So what looked like one step in the chemical equation is actually 3 steps. Well, these 3 steps right here is called the reaction mechanism. So I wanted to show you an energy diagram for this process of A going to D. And I know that you don't have this in your notes, but I would like you to draw this energy diagram either at the top, the bottom, or the margins of your notes somewhere, because it's going to be important going forward. And so let me put it on the board here. It says draw an energy diagram for this process of A going to D. And we're going to assume that it's an exothermic reaction. So A going to D is an exothermic reaction. Well, let's draw the energy diagram. You remember from last chapter, we drew a lot of these energy diagrams where we had energy on our y-axis. And really what we're measuring is heat energy called enthalpy. And then we put reaction time on the x-axis. Now, if you look at this reaction, it looks like it's one step, but if you see the mechanism, there's 3 steps. So drawing the energy diagram for this reaction is a little bit different, and that's why I wanted to go over it. So there's 3 steps here. I always remember for 3 steps, we have to have 3 activation energies. So 3 hills. And it's exothermic, so we're going to start up here. And let's put A right there. That's our first reactant. Now, in the first step of the mechanism, it goes to product B. We know there's an activation energy for this process. I don't know exactly what it is, but there's B. Okay? Well, now we're to B, we need to go to C. There's going to be another activation energy. Maybe this is not very tall, and it goes to C. And then finally, C gets changed into the product D, so there's another activation energy, and we end down here at D. So the energy diagram for the whole mechanism looks a little bit different than the energy diagrams we have drawn in the past. Just remember, if there's 3 steps, there's got to be 3 activation energies. Exothermic means that our delta H for this reaction is negative. So heat was released. And yeah, so just be aware that the energy diagrams for these will look a little bit different. All right, here's an example of a reaction mechanism. So we have an overall reaction given here of H of hydrogen plus 2 ICLs goes to 2 HCl's plus iodine. So this is my overall reaction. But the mechanism for this reaction could be a little bit different. And in fact, the mechanism happens in 2 steps. So we call these steps elementary steps. These 2 steps of the mechanism are called the elementary steps. The reason they're called elementary is that they cannot be broken down into simpler steps. They are at the most simple as they get. And so broken down, the mechanism would have 2 elementary steps. Okay, let's look at the reaction mechanism in a little bit more detail now. So elements of a mechanism, we're going to talk for a second about these things called intermediates. When you look at the overall reaction, what I'm putting in a rectangle here, this is my overall reaction in blue. And it looks like we have 2 elementary steps here in the mechanism. But notice that HI is a product in step 1. So it's a product right here. But then it's a reactant in step 2. So notice, it's formed in step 1, but then it's used up in step 2. Because HI is made, but then consumed, HI does not show up in the overall reaction. So if you look up here at my overall reaction here, there's no HI. And the reason for that is that it was made here, but then it gets canceled out in the next step of the mechanism. And so that's exactly what an intermediate is. It's something that is made, but then used up, and it doesn't show up in my overall reaction because it gets canceled out. So I think in your books you're supposed to write down the definition for an intermediate. And they are substances that are canceled out in the reaction mechanism. So in this example, the hydrogen iodide here would be our intermediate. Okay. There's this word here, it's called molecularity. Let's talk about what it means for a second. Molecularity. The number of reactant particles in an elementary step is called its molecularity. So again, we're going to look at these individual steps of the mechanism, called the elementary steps, and we're just going to count the number of reacting particles. So, there can be what are known as unimolecular steps, which involve 1 particle. An easy way to remember that is uni means 1. So if you'll make that note, uni means 1. But there's also bimolecular step, which has 2 particles. Bi means 2. So in a bimolecular step, would have 2 particles in your reactants. And finally, there's these called termolecular, which means 3. So there's 3 particles. Termolecular are very rare. You don't see them very often in elementary steps. But here's a slide that will explain what I'm talking about in a little more detail, and hopefully this will make sense. So here's my elementary steps. For this first one, we've just got 1 reactant. So if you've just got 1 reactant in your elementary step, the molecularity is 1, or it's called unimolecular. But if you have 2 reactants in your elementary step, even if it's the same molecule or the same particle here, since there's 2 of them, we say that the molecularity is 2, or it's bimolecular. So again, we'll have 2 right here, but they're different. It's still called bimolecular, or it has a molecularity of 2. Now these final 3 here, they all have 3 reactants, and so they're called termolecular, or the molecularity is 3. And again, they're very rare. Okay, let's look at the rate laws for elementary steps. Each step in the mechanism is like its own little reaction and has its own activation energy and its own rate law. So for every elementary step, it's like its own reaction, has its own activation energy, and its own rate law. So let's talk about that for a second. The rate law for an overall reaction must be determined experimentally, like we've been talking about. You've got to set up the reaction in the lab, let it run, and collect some data about the kinetics or the speed of the reaction. You have to determine the rate law experimentally. There's no way to predict what the rate law will be just by looking at a reaction equation. But the rate law of an elementary step can be deduced from the equation of the step. And here's what I mean. So if this is my overall reaction, okay, this is my overall. It looks like this has 2 elementary steps in the mechanism. And so each elementary step is like its own reaction. It's going to have its own activation energy and its own rate law. And so let's look at the rate law for elementary step number 1. We've got H2 as a reactant and ICl as a reactant. So the rate law is equal to K times the concentration of H2, which is our reactant, times the concentration of ICl, which is a reactant. But also, elementary step number 2 would have its own rate law. Again, because HI is a reactant, that's going to show up in our rate law, and ICl is a reactant, so it shows up in our rate law. So each step can have its own rate law. Now this is a very important point to make in the lesson. The rate determining step. A lot of chemistry textbooks will abbreviate rate determining step as RDS. So if you'll make that little note, the RDS is the rate determining step. So in most mechanisms, one step occurs much slower than the other steps. So one of these elementary steps is going to be much slower. The result is that the product production cannot occur any faster than the slowest step. So you can't get products any faster than the slowest step. The step determines the rate of the overall reaction. So that slowest step determines the rate of the overall reaction because it occurs much slower than the other ones. So here's your definition for rate determining step. The rate determining step is the slowest step in a reaction mechanism. So we're going to look at these elementary steps, and you might get some kinetic data that tells you the rate of the chemical reactions. You're going to look for the slowest one. The slowest one is our rate determining step, which is the slowest step. And it's the slowest step because it has the largest activation energy. So if you look at an energy diagram, if it's got a large activation energy, if this hill right here is very large, that's going to occur very slowly. If the hill is small, then it will go faster. But the rate determining step is the slowest, has the largest activation energy. And also a very important point, okay? The rate law of the rate determining step determines the rate law of the overall reaction. So if you're given a bunch of elementary steps and it tells you which one is the slowest, well, that's your rate determining step. But you also build the rate law of the overall reaction. It's built from that step. All right, now I've got a picture of a freeway here. Okay, let's label these lanes A, B, and C. And I asked you, what is the rate determining lane in this freeway? So which lane is our rate determining lane? And hopefully you're thinking to yourself right now that the rate determining lane is lane C. That's the lane that's going to be going the slowest, especially when all these other cars are merging in. This is the lane that determines your speed on the freeway from that point on. So that is our rate determining lane. Anyway, kind of an analogy to try and help you kind of see a different perspective of what rate limiting would mean. Okay, here's another reaction mechanism that I wanted to show you real fast. Again, this top one is our overall reaction. Okay, so in blue, that's our overall. And it looks like we've got two elementary steps. And I've got some questions for you. First question is, which elementary step is our rate determining step? Which one is our rate determining step? And I hope that you're thinking to yourself right now, because this one is our slowest elementary step, that it is our rate determining step. Okay, here's another question for you. What would the intermediates be for this reaction? Remember that intermediates can be canceled out and they don't show up in the overall reaction. So think about that. What are our intermediates? So if you look here, NO3 does not show up in our overall reaction because NO3 is formed in step 1, but then it is consumed in step 2, so it will cancel out. Is there anything else that will be canceled out? And the answer, yes. NO2 will cancel out with one of your NO2s here, but you still have NO2 because there was another one right here. Okay, so my intermediate is NO3. Now, another question. How many activation energies will you have in your energy diagram? How many hills will you have? And hopefully you're saying that since we have two elementary steps, we're going to have two activation energies. Now here's another question. Which activation energy hill is going to be the largest? And hopefully you're thinking to yourself, well, because step 1 was the slowest step, my rate determining step, that the first hill, this first reaction, is going to be larger. That's what makes it so slow. All right, and then one final question. Which elementary step determines the rate law of the overall reaction? So which one of these elementary steps is going to determine the rate law for the overall reaction? Well, the rate law for the overall reaction is given right here, so that should be pretty easy. It looks exactly like the rate law for the first reaction, and that's because the rate law is determined by the rate determining step. It's going to be the same for the overall reaction. Okay, I've got an energy diagram here for this chemical reaction. So we look here, we'll notice that the activation energy for the first step is very large. That's why it's so slow. That's why it's our rate determining step, is because there's a lot of energy that has to be given to these reactants so that it can overcome the activation energy barrier. Notice that the activation energy for elementary step number 2 is very small. That's why it occurs very fast. Okay, let's see if there was anything else. The first step is slower than the second step because the activation energy is larger. We got that. The first step is your rate determining step. It's the slowest step, and the rate law of the first step is the same as the rate law for the overall reaction. Okay, so let's talk about validating a mechanism. So validating is much different than proving. You can never, I guess you can't ever really prove a mechanism, we can't see this happening and we don't know for sure, but to validate a mechanism, two conditions must be met. Number one, the elementary steps must sum to the overall reaction. So if you cancel out all your intermediates and it sums up to the overall reaction, that's one way to validate your mechanism. But there's also a second step. The rate law predicted by the mechanism must be consistent with experimental observed rate laws. So if you come up with the rate law in the mechanism and you go and do the reaction and it also occurs that way, then you have likely validated the mechanism. Okay, let's go to practice problem number 23. This one is in your book. And I would like you to answer this question, but there's a number of parts to it. So it says determine the overall reaction. So that's my first thing that I'm asking you to do, is to determine the overall reaction. Then I would like you to determine which step is our rate determining step. So that's number 2 that I would like you to answer. I want you to tell me the rate law for the overall reaction. So that's number 3. And I want you to identify all intermediates in this reaction. So that's number 4. So I want those 4 things answered on practice problem number 23. If you're watching the video at this point, please press pause. Try it on your own. Once you have an answer, then hit play and see if you got it right. Okay, hopefully at this point you've tried it on your own first. And let's see how you did. Here's how I would go about solving this problem. So, number 1, we want the overall reaction. What I do is you just sum these two. So we're going to add these two reactions together. But we're going to look for anything that can be canceled out. What I mean is that if there's any products that will cancel out with a reactant. And let's see here. It looks like B is going to be made in the first step, but then it's used up in the second step. So that's something that can be canceled out. Is there anything else that cancels out? And it doesn't look like it. So my overall reaction is equal to, now I've got 2 A's. So I'm going to put 2A plus, and I've got a B2. Now this B got canceled out, so it's no longer in the overall reaction. And that goes to, it looks like I have 2 AB, so I'm going to put 2 moles of AB. Okay, and that's my overall chemical reaction. Okay, let's go to step 2. I asked you to tell me the rate determining step. The rate determining step is the slowest step in the mechanism, so that would be this step. So my rate determining step is step number 1. Okay, so that was the second thing I asked you to do. The third one is I wanted you to write the rate law for this overall reaction. So my rate law has the general form of rate is equal to the rate constant. Now, the rate law is always going to be determined by your rate determining step. So we're going to build the rate law from step number 1, because that's the slowest one. It looks like we have 2 reactants. So we're going to times it by the concentration of A, raised to some power, which we don't know yet, times the concentration of B2, raised to some power. To determine the order with respect to A and B2, we would have to actually do the reaction and determine the orders experimentally. But for right now, we're just going to leave them as 1. And that's my rate law for the overall reaction. Notice, it would be exactly the same as the rate law for step number 1. Okay, and then finally, I wanted you to identify all the intermediates. So step 4, identify all intermediates. So, My intermediates here are what are canceled out in the mechanism steps. And so B, because it was made in step 1, and then it was consumed in step 2, is canceled out. That will be my intermediate. Now, I want to add something to this. What if I added and asked you on the test to draw an energy diagram for this reaction? Okay, let's do that real quickly. An energy diagram. How many activation energy hills would I have to draw? Hopefully you're thinking to yourself 2, because there's 2 steps. Now I didn't say whether this was an endothermic or an exothermic process. We'll assume it's exothermic, most reactions are. So you're going to have 2 hills here. But notice, because step 1 is the slowest, that's going to be a larger activation energy than your second step. Okay, and it might look something like that. But notice, activation energy 1 here is much larger than activation energy number 2. Larger activation energy, slower in terms of its reaction time. Okay, very good. Let's move on. So let's see if we got those answers right. It looks like we did get the overall. B was an intermediate. The first step was rate determining, and our rate law we did get correct. So very good. Okay, I've got one final topic in this chapter to talk about. It's called a catalyst. So let's look at what a catalyst is. Catalysts are substances that affect the rate of a reaction without being consumed. So a catalyst will speed up the rate of a reaction, but catalysts are not consumed in the reaction, which means a catalyst can be used over and over and over again in the chemical reaction. A catalyst works by providing an alternative mechanism for the reaction. So it kind of provides this other path for the reactants to take to form the products. What a catalyst really does is that it lowers activation energy. So this hill that you see is much smaller if you use a catalyst. So the dotted line would represent the activation energy for a catalyst. The solid line here is just for the reaction under normal conditions without a catalyst. Catalysts are consumed in an early mechanism step, but then made back in a later step. That's going to be very important when we look at these mechanisms. Catalysts are consumed in an early step, but then they're made back in a later step. Here's an example of a mechanism without a catalyst and with a catalyst. So we've got O3 plus O goes to 2 O2s. And it says very slow right here. So there's no catalyst here, it goes very slow. Well, if you put a catalyst in this reaction, it can go faster. Now I wanted to ask you though, looking at this mechanism with a catalyst, I want you to identify the catalyst. Which one of these substances is the catalyst? Remember, go back to this definition. Catalyst is consumed in an early mechanism step, but then made back in a later step. So looking down here, I want you to identify which substance is your catalyst. Hopefully you're thinking to yourself, well, chlorine right here is being used up in an early step. It made it go fast. In a later step, what's happening is that chlorine is being remade. So it's consumed in an early step, but remade in a later step. I want you to look for that as we talk about and show you mechanisms today. Here's an example of a catalyst. What I've got here is a couple of YouTube videos that's going to show you the chemical reaction known as the iodine clock reaction. In the iodine clock reaction, we're just going to take two solutions and mix them together. And what's going to happen when the reaction starts is you're going to notice it changes color to a dark purple. It almost looks black. But this first video is going to show you without a catalyst. So I want you to notice and take a mental note of how long this reaction takes when it starts, how long it takes to actually climb up this graduated cylinder. So you're going to notice it starts down here somewhere, the bottom of the graduated cylinder. And then it's going to climb the tube. And I want you to take a note of how long that process takes. So it takes a second here for him to pour in the solution. And it's just about to start, but you're going to notice at the bottom of the tube a color change. So there it goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Maybe 20 seconds about for that reaction to go from the bottom of the graduated cylinder to the top. About 20 seconds. Now we're going to look at the same exact reaction, but this one we put a catalyst in. So a catalyst should speed up the chemical reaction. Let's see how fast this reaction goes now. Okay, so again, we got to pour in the solution to get the reaction going. Again, when it starts, you're going to notice it at the bottom of the graduated cylinder. It's going to change to that same dark color. But let's take a note now of how long it takes for this to happen once it starts. So there it's starting, so about 1 second, and it's already to the top of the graduated cylinder as fast as he's pouring it in there. So kind of dramatic there. It went from 20 seconds to only 1 second if you use a catalyst. So okay, I want to talk about the energy diagram, how it changes when you introduce a catalyst. So if you look at this energy diagram here, the blue line is without a catalyst. So this activation energy is huge when there's no catalyst. What a catalyst will do is provide an alternative pathway for these reactants where there is a smaller activation energy. Much smaller, which means because there's a smaller activation energy, the reaction can occur much faster. So the reaction goes much faster with a catalyst. So the red line here is with a catalyst, the blue line is without a catalyst. Okay, let's do practice problem number 24. It says to determine the overall reaction, so that's the first thing that I want you to figure out, is the overall reaction. And then the rate determining step. I want you to identify which one is your rate determining step. I want you to write the rate law for this overall reaction. That's the third thing. And then finally, identify all the catalyst and intermediates. So there's your fourth thing that I would like you to do. So if you're watching the video now, please hit pause and try this one. See if you can't identify those four answers. Once you have all those answers, hit play and see if you got them right. Okay, let's see how you did. First of all, the overall reaction. What I would do is draw a line underneath your two elementary steps. And let's see if we can cancel anything out. It looks like my Q2 R2 minus can cancel out. It also looks like I can cancel out the R minus on both sides of the arrow. And is there anything else there that I can cancel out? It doesn't look like it. So now to write the overall reaction, it looks like I'm just left with HQ2R2 plus, well, actually there's nothing else on the left side of the arrow, so that's the only reactant that we have, so I'm going to erase that plus sign. Now let's go to the product side. Looks like I have HR, and we also have some Q2R left. Okay, so there's my overall reaction. That's your answer for number 1. Number 2, you were supposed to tell me the rate determining step. So it did give us a little bit of data here. It said that elementary step number 2 was slow. That means step 2 is my rate determining step. Okay, so there's your second answer. Number 3, I wanted you to write the rate law for this overall reaction. Remember, the overall reaction's rate law is determined by the rate determining step, which was number 2. So we're going to build the rate law based off of step 2. So the rate law is equal to K. Now in step 2, we just have one reactant, Q2R2 minus. That's my rate law for the overall reaction. So that's your answer for number 3. And then number 4, identify all the catalysts. So let's see if we can find the catalyst. My catalyst is, remember that definition, it's used up in an early step, but then it's remade in a later step. So if you look at our mechanism here, it looks like R minus is being used up and then it's remade in a later step. And so my catalyst for this reaction is R minus. Notice when it's used up, the reaction goes very fast. That's what a catalyst does. It speeds up the chemical reaction. And my intermediate is something that cancels out in the mechanism and it doesn't show up in the overall chemical reaction. If we look here, Q2R2 minus is being canceled out. It doesn't show up in my overall reaction. So Q2R2 minus is my intermediate. All right, so hopefully you got all of those and that makes sense. Let's see if we got them right. Yeah, it looks like we got the overall reaction. R minus was the catalyst. Q2R2 is an intermediate. And our rate law was built off of the rate determining step. So we did get it right. Very good. All right, catalysts can come in 2 forms. They can come in what is called a homogeneous form. Homo, when you see the word, the prefix homo, I hope that you're thinking that it means same. If you'll remember that, it will make a lot more sense. So homo means same. A homogeneous catalysts are in the same phase as the reacting particles. For example, if chlorine is our catalyst and it's in the gas phase, and our reacting particle ozone is O3, it's also in the gas phase. Notice, they're in the same phase, same meaning it's a homogeneous catalyst. But catalysts don't always have to be in the same phase. There are what are called heterogeneous catalysts. Hetero means different. So if you remember that, this is easy to remember. A heterogeneous catalyst are in a different phase than the reacting particles. And here's an example of a heterogeneous catalyst. In your car's exhaust system, there is what is called a catalytic converter. The catalytic converter takes gases that come out of your internal combustion engine, and these gases might be harmful to the environment and to people. What the catalytic converter will do is convert these to maybe less dangerous pollutants and less dangerous chemicals. Now these are still probably not the best for the environment, but they're less harmful than what they were before the catalytic converter. So if we look here, we had carbon monoxide, we had a nitrogen dioxide. At the end, we're left with nitrogen, which the air we breathe is mostly nitrogen, water, which is not harmful, and we've got CO2, which is a greenhouse gas, but it did clean up the exhaust quite a bit there. So anyway, example of a homogeneous and a heterogeneous catalyst. Okay, another slide showing the same thing. Here's my catalyst, is this yellow dot here, and my reactants are also in the gas phase. So they're both in the gas phase. It's called homogeneous. Now over here, heterogeneous, the catalyst is in maybe a solid phase here. My reacting particle is in the gas phase. So they're different phases, heterogeneous. Here's another slide showing the catalytic hydrogenation of this molecule here. Hydrogenation just means you're adding hydrogens to it. And so the catalyst might be this surface right here, and when the molecule hits it, it allows for these hydrogens to actually bond to the molecule and hydrogenate it. In the end, we've added a bunch of hydrogens to that molecule. So this catalyst just makes that process happen a little faster. Okay, I would like to finish up by talking about enzymes. Enzymes, you might have heard of these things before. If you've taken biology, you've definitely heard of enzymes. They're very important molecules inside living organisms. So let's review. Because many of the molecules that make up life and are involved in chemical processes of living organisms, they're very large and they're complex. Most biological reactions require a catalyst to proceed at a reasonable rate. Like our digestion, there's a lot of enzymes and catalysts that are required to make our metabolism function at a rate that keeps us alive. An enzyme, you're supposed to write down the definition of an enzyme. An enzyme is a protein molecule that catalyzes biological reactions. So enzymes are catalysts. Enzymes are catalysts. The only difference between an enzyme and a catalyst is that an enzyme is a biological catalyst. Bio meaning life. So if you have a catalyst that's involved in a living organism, that's called an enzyme. If it's not in a living organism, we call it a catalyst. So again, if it's in a living organism, we call it an enzyme. If it's not in a living organism, we call it a catalyst. But they do the same thing. They make reactions occur faster. So enzymes work by absorbing the substrate reactant onto an active site that orients the substrate for the reaction. And I'll show you what I mean in this next slide. In fact, catalysts and enzymes, they work kind of the same way. Here's my enzyme. This blue, it looks like a puzzle piece here. How an enzyme or a catalyst lowers the activation energy? Well, it provides a surface here. This is called the active site. This surface which provides a better surface for the reacting particle, this is called the substrate, to bond to, and it makes these molecules have the correct orientation every time, and it just lowers the energy needed to for this reaction to form the products. And so every time these reacting particles collide, because of this surface, it helps them to collide with the correct orientation and form the products, and it doesn't require as much activation energy. So it kind of works as a lock and key mechanism. This would be the lock here, and the key fits perfectly. It helps produce the products at a much faster rate than otherwise. Okay, that's it for Chapter 5, and I hope that we've learned something about kinetics. Today, I hope we've learned something about reaction mechanisms. But to give you some more practice, in your student workbook, there is a worksheet that I would like you to do right now. It's called Reaction Mechanisms Worksheet. Again, let's go to your student workbook. It's called Reaction Mechanisms Worksheet. Let's get that done right now, and hopefully this video helped.